Welcome to Solvent Extraction. So in most analytical measurements, we must separate, identify, and measure one or more components from a complex mixture. Now Chapter 22 discusses the fundamentals of analytical separations, and Chapters 23 through 25 discuss specific methods. So here we're going to start out by discussing solvent extraction. Extraction is the transfer of a solute from one phase to another. And note that phase here refers to a distinct region with a different composition than another region of the system. Not necessarily different phases of matter in the sense of solid, liquid, gas. They may be two liquid phases. Many times they're two liquid phases for a solvent extraction, a simple solvent extraction like is shown over here. We have two liquid phases. That's two separate phases. So we may have something like, in this case, colored water. This is just colored green food coloring in water. And then we have some oil, like some vegetable oil on top. And so we've got these two clearly distinct regions. One is an aqueous phase, one is an organic layer that's sitting on top. That is, we may be talking about different physical phases of the same substance, for example, liquid water and water vapor, or the same physical phase of different substances. For example, two immiscible solvents, as in liquid water and a liquid hexane. We usually perform an extraction to either concentrate the analyte or to isolate the analyte from interfering species. Now suppose we have a solute S partitioned between two phases of immiscible solvents. So we've got our S, we've got some down here and some up there, and they're at equilibrium. The partition coefficient K is the equilibrium constant for the reaction where we have our solute in phase 1 that transitions to our solute in phase 2. So it's crossing that phase boundary. And our partition coefficient K there is equal to the activity of our solute in phase 2 divided by the activity of our solute in phase 1. And this is going to be approximately equal to the concentration of our solute in phase 2 divided by the concentration of our solute in phase 1. And note here that in order to simplify the notation, this I in SI, so here and there, refers to the phase, not a subscript in a chemical formula. Also note that hereafter we're going to ignore the effect of activity coefficients. So instead of writing K is approximately equal to the concentrations, we're going to say K is equal to those concentrations. It's up to you to remember that these are really approximations. So let's suppose that solute S in V1 milliliters of solvent 1, let's say this is water, is extracted with V2 milliliters of solvent 2, let's say toluene. M is the total number of moles of S in the system, and Q is the fraction of S remaining in solvent 1, so the water phase, at equilibrium. That means that the concentration in molarity of S in solvent 1 at equilibrium is then Q times M divided by V1. And that means that the concentration of S in solvent 2 is then the quantity 1 minus Q times M divided by V2. And this means that the partition coefficient, when we replace our concentrations here, concentration in phase 2 and phase 1, with these guys, note that then we've got M that cancels here. We've got the V2 over V1, but those are both in the denominator, so we can invert those and we end up with V1 over V2 times the quantity 1 minus Q divided by Q. We can then solve this for Q. So this is the fraction of our solute S in solvent 1 after one extraction is Q. And that equals V1 divided by V1 plus K times V2. That is, the fraction of S remaining in solvent 1 depends upon the partition coefficient and the volumes of the two phases that we have, the two solvents. So if we then remove solvent 2, that was the toluene, and add fresh solvent 2, toluene, the fraction of solute in solvent 1 at equilibrium after the second extraction then is the fraction of S in solvent 1 after two extractions. It is Q squared, and this is going to be the square of our expression on the last slide, so the square of V1 over V1 plus KV2. And note that we've assumed that the volume of solvent 2 for the second extraction is the same as that for the first extraction here. If it's not, then we won't have this quantity squared, and then we'll have a different volume here for volume 2. It'll be volume 2 prime and volume 2 double prime. We can expand this then to the general case of the fraction of solutes in solvent 1 at equilibrium after n extractions. So the fraction of S in solvent 1 after n extractions is Q to the nth power is equal to the quantity of V1 over V1 plus K V2 raised to the nth power. And again, we're assuming that all of those volumes of that second phase are exactly the same size, the same volume. So suppose that solute A has a partition coefficient of 3 between toluene and water. That is, at equilibrium, the concentration of A in toluene is 3 times the concentration of A in water. And further suppose that 100 milliliters of an aqueous solution of 0.01 molar A is extracted with toluene, which is going to be more efficient, extracting once with 500 milliliters of toluene or extracting 5 times with 100 milliliters of toluene each time. That is, what's the fraction remaining in the aqueous phase after each procedure? So after we've extracted once with just a single 500 ml volume of toluene, or successive extractions 5 times with 100 ml volumes of toluene. So with the single 500 ml extraction, the fraction of S in solvent 1 after 1 extraction is equal to Q. That's equal to V1 over V1 plus K V2. V1 is 100 mils, K is 3, and V2 is 500 mils, and that gives us 0.062, or about 6%. With the 5 100 mil extractions, we now have Q to the 5th power times that same expression, where now we're going to have different volumes of V2 here. So instead of 500 mils down here, we have 100 mils. But when we raise that to the 5th power, we now get 0.00098, and this is about 0.1%. So you can see that we get a lot less remaining when we do the 5 successive extractions. And this means that these 5 successive extractions are significantly more efficient at removing our solute A from that water phase. So with our single 500 ml extraction, we get 6% remaining. With the 5 100 ml extractions, we get 0.1% remaining. And this means that performing more extractions with smaller volumes each time is more efficient. So if the solute is an acid or a base, its charge will change with pH. And a neutral species is generally more soluble in nonpolar solvents, and the charged species is more soluble in polar solvents like water. And this means that we can tune the pH to alter that partition coefficient between the organic phase and the aqueous phase. So let's examine a basic amine with neutral form B and conjugate acid BH+ with acid dissociation constant of Ka. And let's further suppose that B has a partition coefficient K between aqueous phase 1 and organic phase 2, and BH+ is insoluble in phase 2. Essentially, because it's charged, the partition coefficient for BH+ greatly favors the water phase. This means that the distribution constant D is defined as the total concentration in phase 2 divided by the total concentration in phase 1. And the distribution constant for our system then is the concentration of B in the organic phase, phase 2, divided by the total concentration in the aqueous phase, which is the concentration of the neutral basic form plus the concentration in the acidic protonated form, that charged species. And again, we essentially have a 0 concentration here in the top, in that organic layer. So remember that the partition coefficient is equal to concentration of B2 divided by concentration of B1. So these are the concentration of our neutral species in the organic phase divided by the concentration of the neutral species in the organic phase. So this term does not include the concentration of our base in the protonated form. But remember that Ka, the acid dissociation constant, is equal to the concentration of hydrogen ion times the concentration of our base divided by the concentration of our conjugate acid. And all of these are the concentrations in that aqueous phase, so that's what these subscript 1s are for. So substituting these into our distribution constant expression gives us this, which then simplifies to K times alpha B where alpha B is the fraction of weak base in the neutral form B in our aqueous phase. Now, charged species are generally more soluble in water than in organic solvents, and so to extract a base into water, we need to use a pH low enough to convert our B into BH+. To extract a base out of water into an organic solvent, we need to use a pH that's high enough to convert our BH+ into our neutral species B. To extract an acid into water, we need to use a pH high enough to convert our uncharged acid into a charged conjugate base, A-. And to extract the acid into the organic solvent, then we want to use a pH low enough to convert our conjugate base A- into HA. So because charged species are more soluble in water than in organic solvents, we need to remove the charge from our charged species to extract it from water into the organic solvent. And one way we can separate metal ions in aqueous solution from one another is to selectively complex one ion with an organic ligand and extract that complex into an organic solvent. We can use weakly acidic ligands such as dithiazone over here, 8-hydroxyquinoline, and cupferrin. When these bind to the metal, then they lose a proton. So we have our protonated ligand losing a proton to become L-, and then some number N of L- will react with our metal ion here, Mn+, to form our metal ligand complex. The acid dissociation constant of our ligand is here, and then beta here is the formation constant of our metal ligand complex. Now suppose that virtually all of the metal in the aqueous phase is in the form Mn+, that means it's charged and not complexed to the ligand, and all of the metal in the organic phase is in the form Mln, which means all of the metal in the organic phase is complexed with the ligand to make it uncharged. And that means that now we have a case that looks something like this. We've got our dense organic phase, perhaps this is trichloromethane down here, and up on the top we've got our aqueous phase. You can see that in the aqueous phase we have a couple of equilibria occurring. We have an equilibrium here between our ligand and proton being protonated or deprotonated. We've got then our ligand reacting with our metal ion to form the complex, and then this large arrow down showing that that metal ligand complex is much more soluble in our organic phase than it is in the water phase. And we also get our protonated ligand to dissolve into the organic phase. The partition coefficients for the ligand and complex then are given here. So we have the equilibrium between the protonated ligand in the aqueous phase and the protonated ligand in the organic phase. That partition coefficient K sub L is equal to the concentration of our ligand in the organic phase divided by the concentration of our ligand in the aqueous phase, and these are both protonated ligand. We also have the equilibrium between the metal ligand complex in the aqueous phase and the metal ligand complex in the organic phase. So across that phase boundary, that partition coefficient Km is equal to the metal ligand complex in the organic phase concentration divided by the metal ligand complex in the aqueous phase concentration. And then that distribution coefficient is the total metal concentration in the organic phase divided by the total metal concentration in the aqueous phase. And that's going to be approximately equal to the concentration of our metal ligand complex in the organic phase divided by the concentration of our metal ion not complexed in the aqueous phase. So we can then combine these two equations to give us this equation down here, where we have the concentration of our metal ligand complex in the organic phase is equal to K sub M times the concentration of our metal ligand complex in the aqueous phase, which is equal to K sub M times beta times the concentration of our metal ion in the aqueous phase times the concentration of our ligand in the aqueous phase. We can then solve the acid dissociation expression for our ligand for the concentration of the deprotonated ligand in the aqueous phase, and then substitute that into our earlier expression here, there. So we plug that expression in here, and we rearrange to get this, and now we can plug that value into the distribution coefficient expression, and that gives the distribution coefficient is approximately equal to K sub m times beta times the nth power of our Ka times the concentration of our protonated ligand raised to the nth power in the aqueous phase divided by the hydrogen ion concentration in the aqueous phase raised to the nth power. But most of our protonated ligand is in the organic phase, and that means that we can substitute the concentration of our protonated ligand in the aqueous phase with the concentration of the ligand in the organic phase divided by the partition coefficient of our ligand, and that means that now our distribution coefficient looks like this, and thus the distribution coefficient for the metal ion extraction depends upon the pH and the ligand concentration. So let's go back and look at that again. So we've got the distribution coefficient depends upon the pH because we've got our concentration of hydrogen ion here, and it depends upon the ligand concentration there in the organic phase. Now we can often select a pH such that the distribution constant is large for one metal and small for another metal. For example, we have here a chart plotting the percentage extracted as a function of pH. And you can see that for different metals, these curves are approaching 0 and 100 at significantly different pHs. And thus, if we want to, say, separate tin from lead, we're going to use a pH somewhere in between there. And that was solvent extraction.